Looking at faces, I know several of you are coming back again, so welcome back. And those who are coming for the first time, welcome to our institute. And this is a mathematics institute, but we have a small activity in the area of, say, statistics, finance, data, all together. A small activity, but as part of that, this is a major event for us. Of course, in association with ISI and support from ISBIS and Indian Bank for some of the activities. I do hope you enjoy the sessions, and let's start the first session.
Let me just say 2 words about ISBIS, and then a couple of sentences, and then we'll move on. ISBIS is an association of the International Statistical Institute, which is really a global organization, and I am especially trying to get people in India involved, because there aren't many international associations with strong people internationally that puts a global emphasis, and I am involved in this for this reason and this reason only. It has many associations. Unfortunately, it doesn't have a bio one. I don't know why. But one of the associations is this International Society for Business and Industrial Statistics. Some of us in this room are involved in ISBIS in one way or the other. N. Balakrishna, who is from Cochin University, he is on our council. He's a council member at ISBIS. And Kathy Enser, who is giving our plenary talk tomorrow, she's from Rice University, but she is the editor of the book, of the journal of ISBIS. It's called Applied Stochastic Models in Business and Industry. It's a great journal, especially people in finance stat intersection. You should strongly consider sending your best articles, as our editor-in-chief likes to say, to ASMBI. And Rituparna is an AE in that journal. So you have contacts here that can tell you more information. And I'm hoping that later on some of you will reach out to me or to any one of us to see how you can join this organization if you are so inclined. All right. So that's my ISBIS hat. And of course, we are very grateful for ISBIS because through a World Bank fund, we are able to support conferences like this, whose intent is to do capacity building, to bring people to talk together about the latest in certain areas. All right, so I thought I would give a talk on one topic. I first thought I would do it on 2 topics, but I don't think we will have time, so one thing is good. Here is my email address. If anyone would like to reach out to me, please feel free. Okay, so I'll give you a brief introduction to this problem of how we can handle durations between events that may be user specified in intraday data, so intraday financial data. And then I'll talk about the specific model that I will be using for modeling this intraday inter-event durations. But then I'll also say that there is a huge area that is open in this respect. We ourselves have done just preliminary look at statistical properties of certain models, but to my knowledge, no one has taken them and looked at their empirical importance in these areas. So if any of your PhD students, or if you are a PhD student looking for a nice topic, an empirical topic with some theoretical underpinnings, those are some directions that might become useful. The particular method that I will be using, even though I'm usually a very, very parametric modeler, parametric Bayesian modeler, the type of approach that I want to talk about is a penalized estimating function approach. The estimating function approach has a long history in India because Professor V.P. Godambe, who is associated with Pune University among other places, was the architect, along with Jim Durbin. He was the architect of this estimating function approach. So we started out by doing this, and the person that introduced me to this area was Kavaneshwaran. He is at the University of Manitoba. So for the past decade or so, he and I have been exploring the use of the estimating function approach in time series modeling. That is my area of interest. Our latest contribution to this is to intersect this estimating function approach with ideas from lasso and sparsity ideas, and that is why we have constructed something called a penalized estimating function approach. You will see when I give you the talk that I will be talking about a very, very special type of penalty using the SCAD penalty, but then that again is a huge area, right? We don't know which of the non-convex penalties, for example, might be useful, and there might be a way to beat these kinds of things for finance by exploring that area as well. The last topic also has many open areas. We are using this penalized estimating function approach to see if we can detect breaks, structural breaks in this time series data of durations. And of course, you can do this for any time series, but my focus will be on this particular framework. And again, people know there are many different ways to do this. I'll mention a few things as we go along. So this is a nice area. It has a strong intersection with statistics, and it's also big data, right? Because some of this, if you look for a whole year even of intraday data, it's like 6 billion records. And so you also have to do some finessing when you're pre-processing this data, and that's why we all have grad students who know Python, and then they do all this and bring us the data. So this is joint work with my grad student who is now working in an industry in Boston. Jian Zhu is an assistant professor at WPI in Massachusetts, and Tava is at the University of Manitoba. Some of us know him. Okay, so when you think about high frequency, I mean, I'm talking about transaction by transaction data. We all know that if you can get your hands on it, that's a rich way to do modeling. By the way, it's not easy to get this data. Jian Zhu, whom I introduced to Rituparna as well, got this data as part of his startup money when he joined WPI. It cost him about 20 or 25K in US dollars. But anyway, we have this data now for 13 years or so that he has, and so we are able to use it for different types of modeling. So one of the things we wanted to do was to be as distribution free as possible, because it is very hard, as you will see in the model, to become, to say, okay, the errors follow an exponential distribution or a log normal. It becomes very hard, and it's not easy to model check those. So one of the goals was we want to do accurate modeling, but we want least restrictive assumptions, but we want to consider inter-event durations. I'll explain what that is in a minute. Now, people in finance know that different stocks, if you think about things on the S&P or something, they have different liquidities, right? And so the patterns that are manifested in the durations will depend upon the liquidity of the stock. And we also know that there is this diurnal pattern, and I'll explain what that is in a minute. So I'm just saying that all this has to be kept in mind when you're doing the modeling. You can use some of it to your benefit, and some of it is like a nuisance that somehow has to be corrected, and then we move on. Okay, so we are going to take the stock prices, and we got this from the Wharton Research Data Services, the WRDS. And so what is an event? An event occurs when, let's say for us, the event occurs when the change in price between two successive transactions on a stock exceeds a certain threshold delta. So the user gives me delta, so delta is 0.005 or something like that. So once the user gives me delta, and then I would look at two successive prices of that particular stock, and then I will declare that an event has happened if that price change exceeds delta, right? And then many people have asked me, should you look at positive, a change in the positive direction only, negative direction only? Lots of adaptations can be made, and other people have said, why don't you look at changes in volume? Yes, anything can be done. You define an event and tell us what the event is, and then we define the durations between that event. Okay, so we took data from June 2013 just to test all our models, and that's the figures you will see is from this data. And we picked just 4 stocks. Bank of America is a very liquid stock. GE and IBM are moderately so, and 3M is like a low liquidity stock. So we just picked 4 stocks that seem to have different patterns, and we worked with these things. So as I said, suppose T sub I is the time, for at which an event happens, right? And the previous time that event happened was at time t minus 1. Di is the time difference between those time points. So these are clock times. Ti is a clock time, Ti minus 1 is a clock time. I take the difference between those two, and that is the duration between the ith time that event happens. So the first time the event happens, I'll show you a picture. So for example, transactions will come like this, right? So on the x-axis you see the clock time after the market opens, and then you keep observing the event, and then when you go and cross a certain threshold, depending on the delta, you mark that point as I equals 1, I equals 2, etc. So the random variable is actually the duration now. We also wanted to early on filter out the effect of this diurnal effect. Diurnal effect is something that is even people like me who don't really trade know this thing, right? There is high trading intensity. So intensity of trading is very high, which means the durations will be very small, right? Because likely to be small. So there are shorter durations during the opening of the market and the closing of the market, and lunchtime is usually slow. So that's called the diurnal effect. And most people, including Ryu Save from Chicago, who has written this book on applied financial time series and all, people just get rid of this because we are not interested in this. We want to find the patterns and durations modulo this effect. We really don't want this diurnal effect to be modeled in every time we model something. So there is a very simple regression type of method to take care of this. I haven't even shown you the formula, but it's so simple, and I'm happy to talk to anybody to say what we did. And there is also a literature on this. Other people have done other things to take out diurnal effect, but we just did what Rusey's book talks about. So what we do is we basically fit that effect out through a regression and get the residuals after fitting that simple model, and the resulting adjusted durations is what I'm going to be modeling, and I'm going to call that x sub I. So di are the raw durations that come from the clock times, and then I filter out the diurnal effect and I get the xi, which are the adjusted durations. And so just to give you an idea, this is for Bank of America. This is for Bank of America, just chose a particular day, 2 days, right? So the upper, these are durations, remember I said the durations would be shorter in the beginning and the end. So you have the raw durations, and then the middle is that say curve that we are fitting, and then we adjust it and it looks slightly better. You're not going to get a uniform thing. I mean, there are still things that remain, but we are modeling the one at the bottom. That's the thing. And if people want to do something better, you can certainly improve on this. Okay, so this is the data. Okay, so we have these raw durations. We have them like literally for every day for 30 years, if you wish, on 500 stocks or something. We have a lot of stocks. Yeah. What kind of a model can we use? Our Engel, who is well known for his arch models, also put his hand in this area, because you will see when I show you the model itself, you will see how similar to our arch Garch model this is. So xi's are the durations, epsilon i's are IID non-negative errors, yeah, and they are independent of the history of the process. The history of the process is this f sub I minus 1 x, that's the history of the process. And let's say epsilon I has some mean mu sub epsilon. So the log ACD model is an adaptation of Engel's ACD model. So Engel first came up with something called the ACD model. ACD stands for autoregressive conditional duration. Same idea, that instead of modeling conditionally the volatility of the process as the arch model does, we are actually modeling the conditional mean here based on the past history. Yeah. So here is the model itself. Let's take a look. So x sub I has a mean e to the some latent value psi sub I multiplicative with epsilon I. If mu epsilon is 1 without loss of generality, that mu epsilon can be forgotten. But in practice, it is good to keep that, and that's why I kept it, to remind people that you may not have a mean 1 structure. And then the psi of I, which is our latent, is just the conditional mean of xi given the past. Remember, in the arch model, we will take sigma I squared. Here, we are taking the conditional mean. and then that you are modeling as a function of something unknown. And the particular model that you are using is some intercept omega plus a function of p past lags of log of the durations, adjusted durations, right? And if you just kept that part, it reminds us a lot of the arch framework. And then you're also adding plus the beta j times the past psi I minus j. So this should remind you of the Garch structure essentially, right? And the reason, so the only difference between the ACD model that Engel gave, Engel and Russell, right? Engel and Russell gave, and is that it would just be this. You don't need to take the E of that. The difference is that here by taking this, I'm allowing the latent psi I to be real valued. Whereas if I didn't do that, because of the non-negativity on the left, I need the psi i's themselves to be non-negative. And that puts more constraints on the alphas and betas, exactly like Arch. So these Bhavans and Guyot came and said, oh, what a pain. I don't want to be working with this non-negative psi i's. Can you please make it real? And so they built this log ACD model, which then allows us more flexibility in estimating the alphas and betas. That's the short story of these models. They're quite powerful. And like I said, Tava and I, another student of his, have a paper in the Tokyo Annals, the AISM journal, where we have investigated tons of conditional duration models with long memory, with augmented, whatever, lots of models. So if people want to try some of those for this finance stuff, it's certainly a good idea. And we have never done it and seen which model works better and all that stuff. And of course, there are some conditions that ensure. So you don't need positivity conditions here. You just need to impose any conditions you need for stationarity. So very simple. If you want 1-1 model, it would look something like this, right? All right, so now I have a vector of parameters. These are the intercept, the p alpha parameters and the q beta parameters. And so given the durations, what shall we do? I can either go completely parametric because I know this is a well-defined model. As long as I can specify parametric distribution for epsilon, remember it has to be positive valued, so it can be exponential, gamma, log normal, Weibull. People have tried various things. Recently we did look at, in a simulation study, mixtures of generalized gammas, and they seem to be doing well. But the whole idea here is not to put a distribution on the epsilon. So, you know, apart from simulation-based comparisons, we don't want to touch and say there is a distribution on the epsilon. I'm only going to ask for a few first moments of the epsilon. All right, so but however, it has been done. Conditional maximum likelihood estimation of theta has been done. In fact, this is discussed in Rousseau's book as well as in some of his papers. It's very easy. It's like writing out the Garch likelihood. You just write down the conditional likelihood and then you maximize it, and you can estimate the theta this way. You can get the standard errors. You can do everything. Yeah, predict and so on. But again, our goal is to go distribution free. And we wanted to try to use this martingale estimating function approach that was Godambi-Durbin approach. And the word combined here is a contribution that Tava made a few years ago. And I'll explain what I mean by a combined when we go to the estimating function description. Okay, so like I said, you don't need to tell me if the distribution is exponential, gamma, whatever. You only need to tell me where you think the first 2 moments are or the first 4 moments are, depending on what type of estimating functions you want to use. All right, so 2 goals for me in this talk, in this paper, is to explain to you what the penalized estimating function approach is. And the second is I want to try and use this for structural break detection. This is a retrospective way of doing it. I'll say something about that later as well. So the PEF approach, I just put on one slide the steps, an overview, and then I'll go and tell you a little bit about each part, and feel free to stop me at any time. So the first thing is, what do I have at this point? I have data, I have my exercise within a day, let's say, and then I have a model that I have chosen. So you have chosen a model. You've said, let me use Bhavans and Guyot log ACD model, right? So once you have your model, your theta is specified. You know now what your theta is. You know the dimension of theta and you know exactly what theta is. And that's what I need at this point. Okay, so you're going to construct a suitable class of unbiased martingale estimating functions, right? These are functions that depend both on your data and the model parameters. And then using this Godambe idea, there are going to be tons of them. We are going to find the optimal estimating function in this class of unbiased estimating functions which maximize the Godambe information. So all very parallel to ML that we are all very familiar with. Then is our next step. We are going to penalize it for sparsity, because when I think about sparsity, think about the P and the Q that we have. Forget the Q for now. Let's just stick with the P part, right? Let's just think about like a first part, log xi minus 1 part. What if I want to go a large number of lags for model fitting, but then I want to introduce sparsity to shrink some of those coefficients to 0. And that's all this penalizing does. Okay, and that's a very automatic way then of setting up this problem, so that if I can, instead of doing this optimal EF, and then I have to model select on the P, which means I have to run this EF for many, many values of P, and then I have to use some criterion like a quasi AIC or something I have to use to get the best model. Instead of that, why not say fit a 50-0 model at all times, P is equal to 50, but then use the lasso type of methods to shrink the coefficients to 0. That is what this penalty does, and we use the SCAD penalty, which was introduced by Fan and Lee in 2001. This then, once you get your optimal estimating function, this is nothing more than a set of nonlinear equations that involve your data and this theta. I just solve it. It's hard to solve nonlinear equations, as you know, and then as you have more and more dimensions, it's harder and harder. In fact, R couldn't do it. We struggled and struggled with R, and then we started using a MATLAB package, and then we use R MATLAB to call it. All right, so now we can get the nonlinear equation solutions, and that will give me my theta hat. And then there is a theorem due to Bruce-Lindsay, which tells me something about the asymptotic properties, and then I can get the standard error. I'm really done. That's all I need really. But then there is a little construct that we have. Rather than solving these nonlinear equations, which becomes very irritating really, what if we can do a Taylor approximation on this estimating function itself and derive recursive estimates for this theta hat I? So the estimates will start to look almost like our Kalman filter estimates. That theta hat I will depend on theta hat I minus 1 plus something like a Kalman gain matrix times something. That's how it comes out. And so this becomes very, very fast to run, as you know. It's just, but then of course you need conditions for this Taylor approximation to be valid and all that stuff. So there are niceties everywhere, which is very nice, I think. So this is the overview of this. And once I have the theta hat i's at this point, I am going to do break detection by monitoring these theta i's as it goes over time. All right, so here are the details, a few details, and if it's boring, I can skip the details. So xi is the duration process, and this f is the filtration, which is the history up to time I minus 1. So the first thing I will do, if you were starting this in a systematic way, the first thing I would do is, under the model that you have chosen, I would find the first 4 conditional moments of xi, given the history, right? Easy to do. And so I've shown you in red for the log ACD model, what are those functions looking like. If you choose a different model, it will look different, yeah? The next step is to construct linear. You can stop with linear, or you can say I'll go linear and quadratic. So you want to construct linear and quadratic martingale differences. The first one is very easy. For every problem, as long as the mean exists, you have this xi minus mu I theta. That is the first martingale difference. The second martingale difference is based on the second moment, so it's mi squared minus sigma squared r. Okay, so that construct that, and then obtain their covariances and variances. That's the next step. And remember, some of us want to make all of this automatic, so that if I give it to a friend in finance or something, they don't have to understand all the nuances of estimating functions, etc. They just need to run it for the model specifications that they put in, and that's their contribution, right? That's where they are most interested in. So most of this first part is hard-coded in our function. It's on GitHub. My student put it on GitHub. It is hard-coded. The only soft coding is what you want to give for your model, right? That's the soft coded part. The rest of it is hard coded, and people don't have to worry too much about touching that part of the code at all. So the construction of the combined estimating function goes back to the Godambe theory. Godambe and Durbin talked about this in 1960, that's the first paper, and then in 1985, Godambe described this for a stochastic process, and then a few people have been working with this. This is not a very rich area at all. If you search for articles on estimating function, you will get articles over and over written by a handful of people. But I think what I like about this is, and I think that is because it's done nice theory, it parallels ML theory, it's very, very nice. But then you have to implement it, right? It's not enough to say, okay, this theory exists, here is my optimal estimating function. But then practitioners need to be able to use it. And one of our goals was to bring it into the practical arena, because we now have code that is based on this estimating function, but can be given to a finance person who is looking at intraday data, and they can actually run this code and get numbers out of it that you can work with. Okay. So we have to assume that the conditional mean and variance depend on the same parameter of interest theta, which it does for us. The estimating function, a combined estimating function, looks something like this. Mi is our linear martingale difference, capital Mi is our quadratic martingale difference. There are some coefficient matrices that are unknown and must be obtained. Yeah. Suppose I leave out the second term. Suppose I drop the bi minus 1 capital Mi, that becomes a linear estimating function. If I drop the first one, the ai minus 1 part, that becomes a quadratic estimating function. The combined estimating function is essentially a combination of these linear and quadratic estimating functions in a clever way, because the part of capital Mi that you must use must be the part of the quadratic thing that is orthogonal to the small mi. You know, yeah, it's a little bit of mathematical stuff, but in principle this is what this is. And why would you combine? Why would you make your life miserable by making a more complicated function? It is because theoretically it can be proved that if you use this combined estimating function and calculate an information matrix, the Godambe information matrix, that information is always larger than equal to any of the marginal information. So if you just use a linear estimating function, you may not be garnering the information as much as if you use this combined estimating function. Another thing that we have never done, and I've been bugging Tava about it, is we have never quantized the information gain. We can use theory and show greater than or equal to, but how much greater than or equal to, I don't think has ever been done, and that will be a nice thing for a student to do as a project or something, because you know, why kill yourself if you're gaining like 0.001% or whatever, right? So practically I don't know the implication, but theoretically it is better to use the combined estimating function. Okay, so this is what I meant. We construct an estimating function by combining the linear martingale difference little mi and the quadratic martingale difference part uncorrelated with mi. That's essentially what goes on to get me that form that I have. Okay, I'm not going to go through the derivations and all, but it's pretty straightforward. So the optimal estimating function will look like this. So the only difference between the general form of the estimating function and the optimal estimating function is I start putting asterisks everywhere, and if I put an asterisk everywhere, it means that's the optimal. Okay, so the G star is the optimal estimating function in this class of estimating functions, and so this AI star and BI star must be computable from what you have, right? So it must be something that you can obtain, and there are explicit forms for all of this, and this is the paper that we have, a theoretical paper on models for durations in this AISM paper. So very quickly, this is what it is going to look like. So we had mu I is our first moment. So we take the first partial. Yeah, don't want to go through this too much, but everybody's just must make sure that everything that I have on the right hand side is obtainable. Once I set up my model and the moments and everything, I should be able to calculate all of these things. So all this is hard coded. And then corresponding to this optimal estimating function, I can find the information matrix. Much as we have MLE and Fisher information, we have this theta hat from the EF and the corresponding information. So one can calculate these as well. Now I come to the penalty part. So we were doing all this and we said, why can't we, okay, we actually sent this out as a paper. So I'm just giving you this genesis of how we even thought of penalizing it, right? We sent this for a paper, and at that point, I'm a very classically trained person. So I fit, for different P's, I fit the model, and I got my, what did we use? We didn't quite develop the quasi-AIC at that point, so we just used some measure of comparison, maybe even predictive measure, and then we said based on this predictive measure we would like to choose the PS4 or something. It was actually a reviewer who sent it back to us saying, why are you doing this? Why are you doing it for different days? Why do you have to do within each day? Why are you model selecting? Why can't you just set up a lasso type of thing? It took us a while to figure out which penalty to use, but we thought that even though this is non-convex, it's a good idea to use the SCAD penalty, and so that is what we did. So we obtained a penalized estimate, and those of you that are interested in this, it takes a little thinking, because if you think about how we do it in lasso, etc., we penalize the objective function. Yes, we have to have an objective function, and that is the thing that we would penalize. But here, our estimating function, think about it, you have a log likelihood, right? In our likelihood framework, you have a log likelihood, and then you have a set of normal equations. Our estimating functions is like these normal equations. But generally when I'm doing lasso and all, I will be thinking of putting a penalty on the objective function, which means that whatever is the version of penalty that I'm going to impose on this estimating function needs to be like a first derivative of that thing, right? So you have to be a little careful when you put penalty, because you have to match it to the lasso theory and all, right? So that's all this is. So if you see this prime there in equation 3, if you see a p lambda prime, it's because it's the first derivative of what I would have put on the objective function, and you have to reconcile that that is okay here. That's the only little math that my student had to do to see this was okay. All right, so we defined this objective function. So we actually are taking our optimal estimating function and penalizing that now. And the rest is all just the SCAD definition. You either know it or it's some penalty that is defined, well defined in the literature. You have to make sure all the properties are satisfied. There is one catch. I don't know how much I want to get into this. This will have a singularity at 0. So we usually use a local linear approximation of the SCAD. This is all nothing, we didn't derive this. All this is in the literature. We just took the SCAD stuff that people have done in the literature and we brought it into the GC star. That's all. We have no contribution on extending the SCAD or anything. And then, so corresponding to this penalized estimating function, I can now find my information matrix. And one worry should be, okay, you make it sparse and all that, but what if you, is it likely that you can lose information? I'm not sure. I couldn't think about it logically, but mathematically we can show that the information gain is going to be non-negative. So if I use the non-penalized and then I try to use the penalized, you get this very nice form, and therefore at least I'm not losing by doing this penalizing of my estimating function. So we decided to use this combined penalized estimating function in order to model our durations and time series. And this was the paper. Bruce Lindsay is unfortunately no more, but he's one of the statisticians I really, really like and respect his work. So he has an Annals of Statistics paper where he showed that he didn't talk about penalized, of course, he just talked about the estimating function. If you solve an unbiased estimating function to get an estimator of theta, he has actually given that the variance of theta hat is indeed obtained from the inverse of the Godambe information. So he has written, that's a very nice paper. It's only like a paragraph. This part is just about a paragraph, but I think that is the only place, and Chris Heidi's monograph on quasi-likelihood are the only two places where you can actually find something that talks about the asymptotic properties of the estimating function-based estimates. It's not very widely discussed. All right. Okay, so this page is basically saying now I have a way of getting the standard errors, and since I've already computed the I star G, I can obtain my standard errors, I can code it in, and I have everything that I need for practical implementation. So now I want to solve this stuff, and as I said before, after I get this GC star lambda, I have a set of nonlinear equations. How many of them? As many as the dimension of theta. So if theta had omega, p alphas and q betas, let us say, I will have p plus q plus 1 normal equations, nonlinear equations, and I should solve them somehow. This is what we did in MATLAB. I said I forgot the name. I can find out. Or we can approximate it and do a recursive estimation a la Kalman filter. I like the second part. So I'm not going to show you all the details. I just showed you the recursive part because I want to use that next in my break detection. So we call this some approximate vector recursion estimate. So once again, the way it works, it's just like a one page of derivation, that's all. So the way it works is, I take this equation 3, yeah, and imagine that I'm evaluating GC star, forget about the lambda part even, it's easy, but the first one, right? So you have a theta. You need theta 1, theta 2, etc. up to theta n. You want like estimates at every time point. Suppose you are at theta I. Now you can expand GC star theta I around GC star theta I minus 1. That is my first order Taylor expansion, right? So I'm going to expand it around the previous theta estimate that I have. That's all. So as long as things are differentiable to the extent that I want, there is no harm in doing this. It's easy to do. So that is all that is going on here. And then all you have to do is, once you have the Taylor, you just have to rewrite your terms and you will get something like this. So you will say the estimate of my entire vector at time point I is nothing but whatever I had at my previous time point plus a matrix that is like my Kalman gain matrix. It's a capital Ki for that reason, and then a bunch of terms, right, that falls out from the algebra. If you were not doing penalized, you will not have that last term. That p lambda term will not be there. Otherwise, you now have this term. So this is our recursive, and there is a form for the k sub I, and that's yeah. So this is the one that can be easily coded and run in practice. For those of you who are students and have struggled with R, you know that anytime you have to invert a matrix, you can get somewhere, and you're doing it for a very, very long time series, right? There are something like 60,000 durations maybe in a day. This is really, really high frequency data, right? So if it is a high liquidity stock, I'm looking at 50,000, 60,000 observations within a day, and somewhere something crazy goes on. You're running this code and suddenly it will say something not singular. How on earth do you go and troubleshoot where is not singular? But if you have never used it, try this near PD function. That's all I wanted to say. It finds the nearest positive definite matrix which is close in terms of Frobenius norm. That's all. So R has this nice function. But even that sometimes, okay, anyway, there are hassles in fitting these things is all I'm trying to say. This looks nice and neat, but a lot of sweat and blood of grad students go in sometimes. K would be whatever if the theta by dimension of theta by dimension. So we used P up to 100, 200, like because we were doing penalizing, so we have tried all different things. P is really large, let us say, then it's just like 200 by 200. It's not very big, it's not n. It's just the parameter dimension. Okay, so I'll skip this. This is just tuning parameter thing. Essentially, the penalizing will look something like this. On the x-axis, I have that lambda, the penalty tuning parameter. On the y-axis, I have theta. And just for, we showed omega, alpha 1, alpha 2, alpha 3, up to alpha 10. And I have different symbols for each of these coefficients. And just to show how each of them is stabilizing for different values of lambda, right? and the one that I have shown as lambda of 0.3 in this particular case is the optimal lambda. So lambda selection is it's a tuning parameter, right? One has to select that, and it is this way that it will go. So this is omega. The triangle is alpha 1. The plus, it doesn't show very well, but this is a plus sign. The plus sign is alpha 2, and the remaining are all here, right? And this is the 0, and then, so what do you think I simulated data from for this? I'm telling you it ran well, it's good, right? So remember, if I had an ACD model, I will have an omega. I will have alpha 1, alpha 2, alpha 3, up to alpha 10 in my model. So suppose I simulated data from something there, some p, but I fit a 10, and then I put it into this CAD penalty business. You see what is happening. It is estimating omega significantly away from 0. It is estimating alpha 1 significantly away from 0, alpha 2 significantly away from 0. Everybody else is literally shrunk to 0, right? So this is a picture of simulating durations from a 2-0 model, and then just making sure that it works. And we did tons of simulations like this to make sure things were kosher. Okay, in the last 15 minutes, do I have 10 minutes? In the last 10 minutes, I'll show you how to do retrospective break detection. If this part was clear, that is all this is, because in retrospective break detection, I'm actually cheating a little bit. It's not a very formal QSUM type or a SPRT type of break detection thing. That comes in our next paper, so maybe next year if Rituparna invites me, I'll tell you about that. But this is just a way in which we want to see whether there is a break, a structural break in the data. A structural break could be a change in one of the parameter values. It could be a change in the way the distribution of epsilon, right? It could be a combination of these things. There's many reasons why breaks occur in time series. We cannot distinguish between the type of break, but we are going to tell you whether a break has happened and where it has happened. So this is a week, the week of June 10th, and we are putting dotted lines. We are putting these very clearly. It's more clear. So there are solid vertical lines. This is one. I think here is one. When I can see in this page, here is one. So there are solid vertical lines that are just day dividers. So between Monday, Tuesday, Wednesday, those are the solid lines, right? And then the dashed vertical lines are telling me where my algorithm, which I'm going to show you, detected breaks. So because there is a natural break between days, I would like my algorithm to capture that. And it seems to do it. In addition, if it shows me other breaks within days, then those are breaks that are caused by something or the other, and it's important for us to know where that is. So this is the kind of thing that we would like to detect. For those of you that are familiar with this literature, in this kind of framework, have you heard of Richard Davis's Autopan? I don't know if people are familiar with time series. Richard Davis is a very strong time series person. He's a friend of ours. He's at Columbia University. And he came up with a retrospective break detection method called AutoParm, piecewise AR model. And we are not doing something like that because he is selecting breaks, breakpoints and number of breaks by a minimal MDL criteria. Minimum description length criteria, but we are doing something more along the lasso line here, just in keeping with our way of doing things. Just a little aside. Suppose the structural breakpoints between the jth and the j plus 1th observation is tau j, and you have m of them. Let us say you have m breakpoints. Tau naught is 1 and tau m plus 1 is n. So what we are going to do is all the durations between two successive breaks we will assume follows a piecewise log ACD model. So I have one model, same ACD structure, but I have one model here, a different model here, a third model there, and so on. The dimensions can change, the parameter values of course might change, that kind of stuff. So that's the piecewise log ACD model, right? Notice you can have P sub j, Q sub j, everything. This is our piecewise model. And then we are going to use the PEF function, everything that I described before. Then what I'm going to do is, what do I now have from the PEF function? I have, so I don't know the piecewise model, right? I'm just running my PEF approach, and what I'm doing is I'm getting over I, I'm getting omega hat I. Let's just say alpha 1 hat I. Let's just say we have these two parameters for now. I have it tracking over I, yeah? And then what I'm going to do is, we have in a paper, JASA paper in 2014, and we tried to follow their kind of idea. A breakpoint is identified when this theta hat I is not equal to 0, yeah? And the number of breakpoints is counted by counting the number of non-zero AIs. Let me show you what I am doing rather than this. So this is the find peaks procedure. I have 5 minutes, so let me show you what this is. So, okay, we have the recursive parameter estimates. Like I said, let's just imagine we have omega and alpha 1, just two of them. We have them over I. What I'm going to do is I'm going to fit a lowest curve to the recursive estimates. So I'm going to smooth it, yeah? And let us say L sub I are the values on this smoothed curve, okay? I am going to compare this alpha 1 hat I to L sub I, okay? I am going to compare it, and if there is no turning point, if there is no break point, then the two will be literally on smack on top of each other, else they will be distinct. So it's a very simple idea, and like I said, I'm not very wedded to this, but this is just one idea to do and it works. But we are now working on an online system which is more mathematically oriented, and I like much. So this is it. So our goal is to find a time point for which the PEF estimate alpha hat 1 is most distant from its lowest smooth. I don't know where the picture is coming later. So this is just the description of that. This is just the description of that. It is basically what I told you. Okay, let me oh, I don't have that picture. Those of you who want to see it can come. It's in our paper. I forgot to put it here. Anyway, so this algorithm works well. It's a very simple algorithm. It's mainly almost visual, but it is just an automated version of what we would do visually, I think. So it's not as pleasing as something that is more prospective and online, so that as data comes streaming, I would like to detect a breakpoint. And if anybody is interested, I'm happy to share our tech report with you. It's submitted right now. All right, so what we did do was, like I showed you earlier, it's the same picture as before. Using this procedure, we are able to capture some breakpoints that are in between the days, but then I don't know what that really means, right? So I don't know. So these analytical items appeared about Bank of America on these 2 days. So I sent my student and said, is there any way to find out why exactly we detected a break in the middle of these 2 days? And it was actually amazing that he came back and said that precisely at about the time when we detected these breakpoints, or our algorithm found these breakpoints, there was some announcement apparently that this Bank of America guy made about something to do with some shares. I don't even understand all this, whatever. Okay, and again on the second breakpoint, there seemed to be another news, and then I said, were there any other news that we didn't find? I don't know if my student lied or not, but he said he did not find anything. So it looks like this method works, even though it's just a very, very numerical procedure. So the meat of this is in our approach of the penalized estimating function. And all I'm showing you is some kind of post-analysis that can be done. Once you have those estimates, there are many things that you can do if you wish. And so this paper appeared in Kathy's journal, ASMBI, very recently. All right, so like I said, questions welcome. Thank you very much.
When you penalize it, will it become again an unbiased estimating function?
when you penalize it. Yeah, the lasso itself introduces bias. But to my scared isn't scared.
You're adding something unbiased business is actually it is unbiased for 0.
Correct.
So when you add some b dash theta, c prime was lambda times b dash theta, that will never become an unbiased system.
It's not unbiased.
So what happens that the optimality that we derive is for the class of regular unbiased estimated function, or which class it is now going to be optimal.
That's a good question.
That's one thing. And another thing is like this estimating functions. Basically, you can because in Fan's paper, what he says is high dimensional confidence set, which can be obtained from that equation itself, rather than going to the estimator as such. So you can actually use. So this idea of Godam is really marvelous. In the sense that at that time itself, we really found that the function can be used to come up with a confidence set, rather than solving it and then use the normal approximation, which is supported by Bruce Lindsay's
paper. Yeah.
So that's really
But how do you implement it? What I'm saying is all this looks very nice in paper, and I fully respect everything that has been done. But then you have to bring the theory to implementation, right? That's what we are trying to do. You have to give something in order to realize it.
Well, you mentioned about the effect of the day. At the end of the day, and the next day, when the market changes. See, there are two things. Volatility is very high at the end of the day and early in the morning. So obviously, given all other things don't exist, we should not be able to identify that the day has changed, right? But you said that you were able to identify.
My colleague expressed, go ahead.
But the other thing also, there's more to it because at the end of the day, market has closed, but it's still after market, after our activities. So the closing price on Monday evening may not be same as opening price of Tuesday morning.
I think that is what it is detecting, all the activity that is on the other end of the globe or something. I think that is how we explain this. Exactly what you were saying is the reason why we think it is detecting a change in that parameter. I mean, we need to discuss it, but it's actually arguing, we argued it the same way.
Why scant and why not lasso or elastic?
I don't know. That's what I said. There's a whole area, right? Lasso is very biased. You probably can use adaptive lasso or elastic, anything.
No,
like
lasso is biased.
Yeah.
Elastic net or
you can. Like I said, we just chose the scan.
The reason I'm saying my feeling is you are facing the problem of the convergence and all these things because it's a non-convex optimization, but elastic net is a convex optimization.
No. The thing about the KI happened even without the penalizing. It is just the structure of the, it's the who knows what is happening once in a while, something large. It's a numerical thing. It's not a structural thing. But I completely agree with you. We have no special reason for picking scan. That's a huge area, like I said. In fact, somebody can tell what's the best way to do it. I would love to learn.
Another thing is instead of nonlinear optimization technique, if we apply or if we adopt kind of approximate Bayesian computation like Gatsby is doing, that could be, I think, is much more. I personally feel it's easier than.
So does it need any distributions or anything, or in this particular case? I know how to do ABC, but would it work in this situation? I'm happy to try. ABC. I did think about doing particle filtering. We can just do particle filtering for this whole problem. You don't have to do this. This is just one approach. It'll be huge, but I've tried particle filtering.
No, I'm saying that when I'm fitting the model, so I'm doing it on the historical data. So I'm not doing online. Offline. I'm talking about doing offline, not online.
You mean on the raw data itself, or on once you go through this machinery? You're talking on the raw data itself.
I'm thinking about parameter estimation conversations, and that I can do on just simply on the offline. What I'm saying that I have the data already, I'm doing it.
On the XI. So XI is your raw input,
yes,
right?
Yes.
Yeah, you can do so many things. Like we are trying particle filtering. You can do that.
What is the day with respect to US time, or because then what does beginning of the end of the mean when
9:30 in the mark. No, we always look at 9:30 a.m. when the stock market opens in New York. Yes, that's how these data are reckoned, I think. No, she's asking which time is it, global time. I'm saying it's. Say that again?
Your day ending in New York and day starting in New York is different, say in Tokyo or more east.
That's what Ravi was also asking, right? Yeah.
So what does it mean? Is it everybody's noon?
Apparently it is different. Like I said, I'm not a finance person. Gian is more knowledgeable in that area, and he said something about even though there is activity happening all around the world, I don't know. So it is not a continuum apparently. According to him, it is correct that we are separating the days.
What is a day that's
A day is for us a New York day. Let's say it's a trading day in New York is our day. In
that particular stock exchange.
yeah.
Off day is the whole other time when it is basically being buffered. Even though you can trade any time you want, logging in from your home, you are basically going through a buffer. That buffer gets executed in the first few seconds
In the morning.
So even though the official opening is 9:30, we will see action from 9:15. If you look at our, so I don't know much about the US things, but in our national stock exchange, you will see transactions, a huge number of transactions in the first 15 minutes, which is before the official opening. That's when the buffer is here.
That's why many a time we leave 30 minutes before and in the evening, so
Because
that it
it's
won't
an
happen.
accumulation of the whole overnight
Right.
orders.
Okay, I think we will stop here, go to coffee, and then we can continue the discussion.